In the preceding video library module, we talked about cements and cementing practices. A continuous, competent sheath of cement around the casing is very important to the safe, efficient production of oil and gas from our well.
Now comes the next important step, selectively opening those zones we wish to produce by perforating the casing, cement, and the formation. Perforating is not just a matter of punching holes in the casing. If our well is to achieve its potential, those holes must be deep enough to reach past any formation damage caused by the drilling and cementing process. They must also be of sufficient number and arrangement to allow the formation fluids to flow into the wellbore unhindered. They must be unobstructed by mud or debris, and finally, they must be in the right position opposite the zones we have identified as productive prior to setting our casing. Accomplishing these objectives in a safe and cost-effective manner is the goal of any perforating program. Poor perforating practices can easily make a 200 barrel of oil per day well out of a discovery with perhaps 2,000 barrels of oil per day potential. Good perforating practices can help us maximize the value of the hydrocarbons we've found. In this module, we shall first outline the basic perforating options available to the engineer. We shall find out that achieving the objectives just mentioned may require a few compromises, with the exception of safety, which should never be compromised. We shall also take a look at the work that has been done to relate perforator performance to well productivity, the final measure of our success. And we shall follow the progress of a perforating job, taking a close look at each important procedure. First, let's look at just what perforating options exist.
Cased holes may be perforated in several ways. Using conventional casing guns run into the well on electric wireline through wireline pressure control equipment. Using through tubing guns run into the well after the tubing has been installed. Or using tubing conveyed perforating guns run on the bottom of the tubing string and detonated using mechanical, electrical, or pressure-activated firing mechanisms.
With each of these delivery methods, there is an option of perforating. Overbalanced, with a higher pressure in the wellbore than in the formation, or underbalanced, with a wellbore pressure lower than formation pore pressure.
Also, the delivery system for placing the shaped charges at the proper location via wireline may be categorized as one of three possible types. Retrievable, consisting of a cylindrical hollow steel charge carrier, which is retrieved after firing and may then be discarded, as in the case of scallop guns, or reused several times, as in the case of port plug guns. Semi-expendable, in which case the perforating charges are conveyed into the well on a retrievable metal or wire carrier. Or fully expendable, where the charges and carrier linkage disintegrate on detonation, and only the wireline is retrieved.
Generally speaking, the larger diameter casing guns run via wireline will carry larger charges, and thus give larger perforation diameters and greater penetration depths than the smaller through tubing guns.
Through tubing perforating, however, is a more practical method for underbalanced perforating than using conventional casing guns, and underbalanced perforating can help maximize productivity.
Tubing conveyed perforating seems to provide a means to combine both the larger high-performance guns with the flexible pressure conditions.
So we see that in considering just these perforating features, wireline versus tubing conveyed, overbalanced or underbalanced, retrievable or expendable guns, we already can come up with at least a dozen different useful design combinations to choose from. All this is without yet considering the variety of shape charges available. Let's look at how a shape charge functions.
The shaped charge, or jet perforator, first came into use in the oil field in the 1950s, following the development of explosive technology during the Second World War. The four important components of the shaped charge are the conical metallic liner, the main explosive charge, the primer explosive, and the case that encloses the charge.
Simply stated, The firing is electrically initiated by the detonator or blasting cap via the detonating cord, which in turn sets off the main charge. Explosive pressure on the metal liner causes it to collapse inwardly along its axis, forming a high-velocity jet of fluidized metal. Moving at a velocity of 25,000 feet per second and with a pressure of 15 million pounds per square inch, the jet displaces the casing, cement, and formation, creating a perforation in only several hundred microseconds.
Depending on the design of the shaped charge and the type of materials being perforated, the perforation length is generally about 2 to 20 inches, 5 to 50 centimeters, and the entrance hole diameter about 0.2 to 1 inch, or 0.5 to 2.5 centimeters. There is a zone of crushed rock around the perforation, and the precise shape of the perforation will vary somewhat depending on charge geometry, gun positioning, and target characteristics.
For example, although the exterior of these charges look identical, this charge is designed to give large diameter perforations for easy gravel packing, while this charge is designed to penetrate deeply with a somewhat smaller entrance hole. Here we see a charge that is designed to be run in a 6-inch or 7 1/4-inch diameter carrier, while this charge is made for a 1 11/16-inch carrier. There is quite a bit less explosive power in this smaller charge, but that power can still be focused on maximizing hole size or penetration, depending on the needs of the completion.
The position of the gun in the casing is another important parameter in determining the size of the perforation. Gun clearance is the distance from the casing inner surface to the gun. Penetration and hole size generally decrease as clearance increases.
This issue is particularly important when small diameter guns are run through tubing into larger diameter casing. In such situations, the gun needs to be positioned against the side of the casing to create a single line of deep perforations. This arrangement, called zero-degree phasing, may introduce an undesirable pressure drop in high-rate wells. Phasing the charges at 60, 90, 120, or 180 degrees would reduce this problem, but at the price of reduced penetration and hole diameter when using through-tubing guns.
The third most important factor in shaped charge performance is the strength of the target material. For example, a charge that penetrates 5 inches into the Berea sandstone target shown here will only penetrate 2 inches in a much stronger sandstone. In deep reservoirs where the formation effective stress is great, the penetration depth may be much less than surface tests indicate, and this factor must be considered when choosing a perforator.
Charge performance is also affected by the quality control applied during its manufacture, where precise control of the liner and charge dimensions is critical. The care with which the charges are stored and transported is also quite important. Charges should be stored in sealed boxes until ready for use. Correct alignment of the shaped charges within the charge carrier, whether it be a semi-expendable strip carrier, a port plug gun, or any of several types of scallop guns, is a very important final step in the gun assembly process. The added cost of quality control in manufacture and assembly is a wise completion investment.
We mentioned the 3 categories of wireline perforation systems: steel hollow carrier guns, semi-expendable guns, and fully expendable guns. Let's take a look at some of the advantages and disadvantages of each option.
In the case of retrievable hollow carrier guns, the charges are positioned and sealed within a steel cylinder, surrounded by air at surface pressure. Each charge is aligned with a threaded port plug in reusable guns, or behind a thinner portion of the carrier wall in scallop guns. Semi-expendable guns typically consist of a series of individually sealed charge cases designed to disintegrate after firing, leaving only the carrier strip or wires to be retrieved. In the case of fully expendable guns, only the wire line remains to be retrieved.
The advantages of retrievable hollow carrier guns include high reliability because all components are protected within the carrier, heavier and stronger construction than expendables, permitting rougher treatment and faster running speeds, generally higher temperature and pressure resistance, very little debris left in the well, retention of the explosive force within the carrier, eliminating casing deformation. A positive indication of firing, provided by the condition of the port plug.
On the other hand, even small diameter retrievable guns may have trouble running inside crooked tubing because of their rigidity. The carrier takes up more space, and the charges may have to be smaller than comparably sized expendable guns, and the weight of the gun assembly may limit its length and thus the interval that can be perforated on a single run into the well.
Considering expendable guns, we can say that they are generally cheaper and easier to assemble, are somewhat lighter and more flexible than hollow carrier guns, and size for size generally offer more penetration than comparable retrievable guns that can be run in the same size tubing.
However, expendable guns can deform casing when detonated, leave substantial amounts of debris in the well, and are generally not as sturdy, leak-proof, and resistant to pressure and temperature as retrievable guns. The typical sizes and specifications of casing guns and through-tubing guns are detailed in your manual. In designing a perforating program and choosing a perforator, the engineer must consider the relative importance of hole size, penetration, and shot density. The size of the completion tubular components and the extremes of pressure and temperature are also important to the choice. For example, we may be convinced of the need for perforating underbalanced and through tubing in a given situation. If we suspect serious drilling damage, we may decide to use expendable charges for maximum penetration and accept the risk of gun breakage, extra debris, and possible casing damage. However, if the well is deep and hot, the durability of a hollow carrier may be important enough to bargain some loss of penetration for a higher percentage of properly fired charges. Each situation requires careful consideration of the alternatives. Making such decisions requires that we be able to test commercially available charges and compare their performance, then extrapolate that performance to downhole conditions and its effect on actual well productivity.
Currently, the industry relies on standard testing procedures developed by the API for evaluating well perforators. These procedures include a surface field test carried out in casing cemented within a concrete drum, and a laboratory test carried out using a Berea sandstone target placed inside a special core holder designed to permit flow through the perforation.
These tests do not duplicate bottom hole well conditions precisely, so the data on perforation dimensions and cleanliness are not always useful in an absolute sense. However, if the tests are carried out correctly, the results can be used in a relative sense to compare commercially available charges. Examples of the API test data recording forms are shown in your manual, along with a summary of the API tests themselves.
But the true effectiveness of any perforator is measured in the well's productivity. Attempts to determine the relative importance of perforation parameters on well productivity have led to the development of mathematical models to simulate perforations. As these models become increasingly sophisticated, more is learned about perforation behavior.
Through this research, which is discussed in your manual, we can now make some qualified generalizations about the relative importance of the four basic perforating parameters: shot density, or number of shots per unit length, penetration, hole size, and phasing.
For example, high shot density is considered of greatest importance in anisotropic or laminated reservoirs. Penetration is less important than shot density when drilling damage is minimal. However, in deep damage situations, it becomes critical. Some type of angular phasing is important when high rates are expected, but generally speaking, phasing should not be gained by sacrificing penetration. Hole size is relatively unimportant beyond a minimum of 0.25 inches, unless the well must be gravel-packed or fractured, in which cases hole size is very important.
We should emphasize that obtaining an adequate shot density not only requires that the appropriate number of charges be run into the hole and that they fire correctly, but that the resulting perforations remain unobstructed and open to flow. The effective shot density depends on the type of formation, the quality of the charge, the type of completion fluid, the magnitude and direction of differential pressure, and the flow time allowed for cleanup.
The type of formation will influence the depth of the perforation and the degree of rock crushing.
The charge quality will influence the uniformity of the perforation tunnel and the type of debris that must be removed.
Most importantly, positive pressure perforating can result in plugged perforations. Even though subsequent swabbing may remove some plugging, other perfs will remain plugged once a few perforations are open. If clean, solids-free, formation-compatible fluids are used when perforating overbalanced, the degree of damage can be decreased. However, reverse pressure or underbalanced perforating can greatly enhance perforation cleanup.
Excess underbalance can also lead to problems. Sanding of the well, migration of fine plugging particles through the formation, or on rare occasions even casing collapse. Several researchers have suggested underbalance ranges for different permeability formations and different formation fluids, and these are given in Section 2 of your manual.
In any case, a volume of fluid should be flowed from the well after perforating to remove perforating debris and improve the condition of the crushed zone. Wells should not be injected into before they have been given a chance to clean up.
There are several techniques for achieving a high effective shot density. Underbalanced through tubing wireline perforating, underbalanced tubing conveyed perforating, positive pressure perforating with reverse surging, and positive pressure perforating with perforation washing.
In through tubing perforating, the tubing and packer are run and set in the cased unperforated well. Pressure control equipment is installed and tested. The gun assembly, including the charge carrier, weights, positioning tool, and collar locator, are run into the tubing on a single conductor cable. After firing, the well is typically flowed for 15 to 30 minutes before the gun and/or cable is recovered. It is important to design the degree of underbalance to prevent blowing the cable up the hole due to frictional forces imposed by the flowing cushion fluid.
With tubing conveyed perforating, a hollow carrier gun is run into the well on the tubing string. The tubing may be run dry or partially filled with a fluid cushion to establish the proper level of underbalance. The packer is set and a vent is open to equalize the pressure below the packer with the tubing. The gun is fired using mechanical, electrical, or pressure activation, and flow is immediately established through the vent. The gun may then be dropped into the rat hole for full-bore flow.
Compared to through tubing perforating, we can say that tubing conveyed perforating, 1, allows greater penetration and multiple phasing because larger guns can be effectively centralized by virtue of their size. 2, permits a greater degree of underbalance without risk of blowing the gun up whole. And 3, may be the least expensive option in cases where significant rig time is saved, although the equipment and service may cost more. However, because the gun is usually not retrieved, we can never be positively certain of individual charge detonation, as with wireline conveyed guns. Good charge quality control should reduce the risk of misfires in either case.
The two other types of perforation cleanup techniques listed in your manual first require conventional perforation of the casing in an overbalanced condition using larger guns and clean, solids-free completion fluids. Then, in the case of the perf surge technique, an underbalanced tubing string is run into the well and set with a packer. When a shear disc within the tubing string is ruptured, the perforations are subjected to a sudden surge of drawdown, expelling any debris that may be present due to the overbalanced perforating.
In the perf wash technique, the conventionally shot perforations are washed using a cup assembly that forces clean fluid into one set of perforations and out of another. Generally speaking, tubing conveyed perforating is more consistent in obtaining clean perforations, followed by the perf surge and then the perf wash techniques.
In your manual is a discussion of the important points to be observed when perforating for gravel packing and for fracturing. Gravel pack completions are typically shot with large hole diameters and high shot densities to facilitate the placement of gravel packed sand within the perforations and to minimize producing fluid velocity through the perforations.
Perforating prior to fracturing is typically done with conventional casing guns and positive pressure. Phasing of the perforations may increase the likelihood that the perforations will come close to aligning with the azimuth of formation fracture. When several zones must be fractured, limited entry fracturing is sometimes employed. In this technique, the perforation diameter and number are limited in order to maintain a high bottom hole pressure and break down successive zones.
Penetration, shot density, phasing, and hole diameter are the variables that may be adjusted depending on the particular perforating situation. Generally speaking, a technique that ensures the maximum number of open perforations extending beyond any damage is the best alternative for a natural completion. When fracturing or gravel packing is to be undertaken, perforation diameter becomes important. In the next unit, we shall follow a perforating job as it is performed. For now, please read sections 1 and 2 in your manual and work the appropriate exercises. Most companies that offer perforating services also offer a variety of open hole and cased hole logging services. And much of the basic equipment is the same. The equipment includes the perforating tools themselves, of course, the cable, the sheaths, tension indicator, the logging truck, including a cable winch and electronic control panels, and the pressure control system.
The tools include a casing collar locator run above the perforating guns, which magnetically detects the position of each casing collar as the tool string is pulled up the hole.
Gun weights are sometimes added to help move the tool string down the hole. Remember that the well pressure is acting against the cross-sectional area of the cable. For example, a common cable size of 7/32 of an inch would need a tool string weight of 190 pounds to exactly offset the force exerted on the cable suspended in a well with 5,000 psia at the surface.
The monoconductor cable normally used for perforating is an armored line with several layers of armor and with an insulated conductor core. If multi-conductor cable is used, as is sometimes the case in low-pressure situations, the normal 7-conductor electrical wireline cable is used, with its armor layers and individually insulated conductors.
The sheath assembly is used to suspend the tools over the well and direct the cable from the truck or wireline unit. Between the top sheave and the rig elevators or crane is a tension measuring device which measures the strain on the cable.
Modern perforating and logging trucks include the drum of conductor cable and the winch system to spool it in and out of the well. A depth measurement device for keeping track of the tool's position. Electrical control equipment and a 120-volt AC generator. And also a recording device for displaying the measured log data versus depth on a film strip or for recording it on magnetic tape.
The pressure control equipment is the most important component of the perforating system because it allows the perforating guns to be lowered into the well or retrieved under pressure.
The assembly consists of a blowout preventer, a riser pipe to contain the perforating tools, a flow tube assembly, and an upper seal or stuffing box.
When closed, the blowout preventer seals tightly around the cable, preventing pressure from communicating around the cable with the riser. The riser pipe consists of pipe sections with quick connect couplings. These couplings are designed to let the internal riser pressure work to maintain the coupling seal.
The flow tube assembly provides the offsetting force which prevents well fluid from flowing out of the riser. When cable is moving into or out of the well under pressure, grease is continuously pumped into the small annular space between cable and flow tubes. Because the space is so small, the force required to offset the well pressure can be easily applied.
At the top of the assembly is a hydraulically activated pack-off. The hydraulic pressure compresses a rubber packing ring around the cable in an emergency to prevent cable movement and seal up the assembly.
In normal perforating situations, the pressure control assembly is either bolted to the blowout preventer stack of a drilling rig or bolted to the top flange of the tubing head or Christmas tree in through tubing perforating. The equipment is pressure tested after it's installed.
After taking the necessary safety precautions to prevent stray currents from accidentally detonating the charges, a voltmeter is used to check for voltage between wellhead and truck. The casing, rig, and truck are grounded together, and the unit power sources are turned off.
After the guns are assembled, a special procedure is followed by the service company engineer to carefully arm the charges with the blasting cap used to detonate them. The cap is held in a specially designed safety tube while the arming is accomplished.
Of course, the perforations must be correctly positioned in the well opposite the formations we wish to produce. Generally, we have some type of open hole log which indicates the productive formations and the depths at which they were found. These depths are measured relative to the Kelly bushing of the drilling rig on location when the well was logged. When we wish to perforate, the hole will have been cased and the rig may or may not be on location. So how do we pick the correct point to perforate?
Normally, we first run a cased hole log such as a gamma ray or neutron log, along with a casing collar locator. This log, called the Perforating Depth Control or PDC log, relates the depth of the formations behind pipe to the casing collars.
This log is then laid over the open hole reference log, which has the desired perforations clearly marked. The radioactive trace is carefully matched and checked by shifting up and down to avoid correlating the wrong formations. The marked perforation intervals are traced onto the PDC log.
Also, remember that the casing collar locator is several feet away from the radioactive tool. This difference must be compensated for within the electronics of the system through a memorizing feature, or else by hand on the PDC log.
With the perforating depth control log in hand, we now have a relationship between the formations to be perforated, the desired perforation intervals, and the casing collar depths. Next, the gun assembly must be carefully measured and sketched, noting the distances from the casing collar locator to the top shots of each charge carrier and the length of each gun. The depths at which the casing collar will be located when the charges are positioned correctly across the intervals to be perforated must be noted for each gun.
The gun assembly is introduced into the riser and the pressure control assembly is sealed. A grease seal is established in the flow tube. The blowout preventers or Christmas tree swab valve can now be opened when the gun assembly is ready to be run into the well.
Now, in order for the guns to be positioned correctly across from the intervals we wish to perforate, we need to correlate the casing collars measured by the gun assembly with those on the PDC log. Here is where a few odd-sized casing joints run in the vicinity of the productive zone will be helpful in distinguishing one collar from another.
Starting below the perforating depth, the collars are logged up the hole and the log is correlated with the PDC log. Any necessary depth correction is made to the odometer. The collars are logged again, and the match checked by shifting the log one collar length in either direction. With a gun assembly on depth, the collar locator is positioned at the designated depth and the gun is fired.
If the well is perforated underbalanced through tubing, the placement of the pressure control assembly on top of the tree allows the well to be flowed for a time before removing the gun and cable.
If a retrievable gun is used, the engineer should verify, after retrieving the gun, that all the charges have fired. An inspection of the port plug holes, or scallops, will indicate if the charges have fired properly. A round hole near the center of the port plug, or scallop, indicates that the charge was correctly aligned and properly functioning. Any charge debris left in the carrier should be relatively small fragments. Practically whole charge cases indicates low order firing of the charge.
As with any completion operation, thorough job planning is a prerequisite to a successful perforating procedure. And the first step in planning a perforating job is to accumulate the necessary data.
Of primary importance is information on the well tubulars, specifically casing or liner size and weight, tubing size and weight, packer type and pressure limits, wellhead connection, and pressure test specifications for tubing, casing, and wellhead.
Other conditions that must be specified or estimated include expected bottom hole temperature, formation pressure and bottom hole pressure desired, formation and wellbore fluids, fluid levels in tubing or casing, surface pressures, pressure and rate limits for surface facilities, and the need for H2S equipment, if any.
Of course, the open hole log used to pick the perforating intervals will be needed, with the intervals clearly marked and the depths recorded. The order in which multiple intervals must be perforated is also important. Your manual has some additional suggestions on choosing a perforating service company and ensuring good shape charge quality. Be sure to read over these points in Section 3 of the manual. For now, let's take a look at another perforating alternative, tubing conveyed perforating.
The primary advantage of tubing conveyed perforating is that it provides a method for combining the high performance of large guns with the opportunity to perforate highly underbalanced.
This method also allows long pay intervals to be easily perforated because gun length is not constrained by weight or riser height.
And highly deviated wells are easily perforated in this manner, since the guns are pushed down the casing.
The basic tubing conveyed perforating assembly includes steel hollow carrier guns, a firing head operated by mechanical, hydraulic, or electronic means, a production vent to permit flow into the tubing below the packer after firing, a gun drop sub, which permits the release of the gun assembly into the rat hole, a production packer, and a radioactive tag sub, which permits a through-tubing gamma ray to precisely position the assembly.
The firing system may be any of several types. A drop bar system, where a steel bar is dropped down the tubing and strikes a firing pin. A hydraulic firing system, where annulus pressure is transmitted to a firing head. A wet connect system, which utilizes an electric wire line run through the tubing. Or a battery drop, which combines the drop bar technique with a battery to provide the electrical firing impulse.
The procedure for running a tubing conveyed perforating system is as follows. First, the guns are assembled vertically in the derrick. Followed by the firing head, or heads if a backup system is used. Next, the vent or production valve. The release sub. And the retrievable production packer are then added, unless a permanent packer is already in the well. In this case, the correct length of sealing elements is added. The entire assembly is lowered into the well and positioned. The packer is set and the proper degree of underbalance established before the guns are fired.
Ideally, the shape charges create deep perforations which are instantaneously flushed clean of debris, as each and every perforation contributes to the flow of formation fluids up the tubing and into the testing facilities. Realistically, though, even the best efforts may require some reperforating to achieve the expected results. But determining if the newly perforated well is performing up to expectations requires some test data to assess the efficiency of the completion. Tools are now becoming available that will allow the engineer to immediately measure downhole pressure, rate, and temperature, even before the guns are retrieved, allowing for the selective reperforation of any poorly performing intervals. So let's summarize. In order to maximize our chances for an effective perforated completion, we should remember perforating underbalance can improve our chances for consistently achieving a high effective shot density. If overbalance perforating is chosen, clean completion fluids are a must. We should use the largest gun possible given any other constraints. Steel hollow carrier guns are generally the best choice even for through tubing perforating, unless the gain in charge size or gun length makes expendable charges preferable. Be certain to flow the well for sufficient time to flush debris from the perforation tunnels. Insist on good depth control techniques and carefully document all perforating activities. Choose a perforating company with a good record of quality control and safe operating practices. In the next module of the 300 series, we shall consider another important completion activity, acidizing. But for now, please read sections 3 and 4 in your manual and work the appropriate exercises. Good luck.